Okay, so in example 4 here, what we have is we're just going to talk about transformations. This is the exact same transformations from unit 1. So we have y equals x cubed, and we're transforming it to obtain this graph here. So to obtain this graph here, the very first thing I'm going to notice is I don't have a dedicated b value. I'm probably going to need to factor in this question. So I'm going to rewrite this equation here. So I'm going to write y equals negative 1/2. Let's use a square bracket, negative 1/2 again, rounded bracket x. So negative 1/2 times x gets you to negative 1/2 x. Negative 1/2 times what would get you back to positive 2. And of course that has to be negative 4 there. Rounded bracket, square bracket, cubed on the outside, minus 4. Now we match up. Let's write down all our transformations starting left to right. So on the very far left there, I notice a reflection on the x-axis. There's a vertical stretch with it by a factor of 1/2. Inside that first bracket we have another reflection, this time on the y-axis, and we have a horizontal stretch this time by a factor of 2. Right after that we have a horizontal translation, and that's going to be 4 units to the right, because it's negative 4 inside the bracket there, and we have this one here, so that's a vertical translation 4 units down. There we go. Let's write down our mapping for this. So it was our standard x comma y. What's going to become of x comma y? Well, let's put together all the horizontals. So we have a negative 2x, and we're moving it 4 to the right, so plus 4, comma, negative 1/2 y minus 4 would finish off the mapping for this one here. In the next example, it's basically saying, given this graph, come up with the equation for it. So a few things that we're going to need to notice about our graph. One, you're going to try to spot as many of your x-intercepts as possible. So I see 1, 2, 3 x-intercepts, and they are at 2, 0, negative 1, 0, negative 1, 0, and of course at negative 3, 0. So I have 3 x-intercepts. If I can try to read the y-intercept, I'll try, but right now this one here, most likely I can read it. I'm going to put a coordinate dot there. My y-intercept is 0, positive 6. Let's write down our equation with multiplicity. So our equation is going to be y equals, and right now I don't know if I have a stretch factor, so I'm just going to throw in a there. If I have to get rid of it later, I'll get rid of it later. Let's write down all our factors. So we have 3 x-intercepts, so that means we have 3 factors. Starting from the left, it'd be x plus 3. Then you'd have x plus 1. And finally, you'd have x minus 2. Let's take a look at all the multiplicities on all 3. So at x plus 3 for a factor, or x equals negative 3 for an x-intercept, this section here, multiplicity, if you take a look between negative 1 and positive 1, this section here is just a straight line, so most likely this is going to be multiplicity 1. Around here at x equals negative 1, again, straight line there, most likely that section there's a multiplicity of 1 as well. Around this section here, clearly if you take a look from this peak down to the valley and then back up, this whole section here looks to be a parabola actually. So this is going to be multiplicity 2. So these multiplicities of 1s there, you don't really need to write them in, but it's always nice to keep track of everything. Let's use this y-intercept to figure out if we actually truly have an a value, so let's plug it in. So our y value is going to be 6 equals a, and I'm going to plug in 0 for all my x values, so that's going to get me to 3, a 1, and 0 here is just going to be negative 2 all squared. Okay, so if you multiply this out, that's 4, 3, that's 12, so now I have 6 equals 12a, and of course solving for a is going to equal 1/2. Let me move that out of the way. So let's rewrite our equation here. So we have our final equation of y equals 1/2 for a, x plus 3, x plus 1, and an x minus 2 squared. Let's double check this equation on our graphing calculator to see if it's remotely the same shape. And again, our grid right now is at 10 by 10. So as long as my calculator is 10 by 10, I'm good, which it is. So let's write down our equation. So another way to write 1/2 is 0.5, by the way, just a quick shortcut to write 1/2. Then we have our x plus 3 and our x plus 1. And that last one was x minus 2. And on there should have been a squared. Let's hit graph. Do we match up? It truly does match up to this exact same shape here. Do we have, if we hit trace, x up 0, y at 6, yep, our y-intercept's still there as well. So yeah, we are good, and this should be our final equation. In this next example, it's going to be a bit tougher, but the very first thing I notice, I have a x-intercept at -4, comma 0. I have another one at 2 comma 0, and a coordinate dot was given to us, so that means we most likely have to use it. This coordinate dot, if you're reading it, should be at 1 5. So that's this black coordinate dot there. In this case here, I'm just going to tell you, you actually cannot read this y-intercept here. Can't read y-intercept, and I'm just going to write that down. Can't read y-intercept. Because to me it looks like it's slightly above that dotted line, so I'm just going to not even use it and say we can't read it. Let's take a look at the overall shape. Well, we have one arrowhead here, and it's in the opposite direction as this one here, so most likely we're looking at an odd degree, so degrees 1, 3, or 5. If I take a look at my x-intercepts right away, I can rule out it's probably degree 1, because right here I already have multiplicity 2. Over here, this looks to be either multiplicity 3 or 5. It can't be multiplicity 5 because we already have this one here, so it most likely is multiplicity 3 here, around 2 there. So let's jot down our equation. So we got y equals a again. We don't know if there's a stretch factor, but we do know that at x plus 4, so that's my first one there, I have a multiplicity of 2. And at x minus 2 here, I have a multiplicity most likely of 3. Let's use this coordinate of 1, 5 to find a. So if you subbed in 1, 5, so 5 equals y equals our a value, and we're going to sub in 1 everywhere. So 1 plus 4 squared times 1 minus 2 cubed. There we go. What does that get us? So that gets us 5 equals, and sorry, wrong one. 5 equals, so this is 1 and 4 make 5. 5 squared is 25. This here is -1. -1 cubed is now just -1. So we have, this is all equal to -25a. To get a by itself, move the -25 over. So that's going to get us to -1/5 overall. So let's rewrite our final equation. So we have y equals -1 over 5, x plus 4 with multiplicity 2, and x minus 2 with multiplicity 3. And again, we should graph this on our graphing calculator to see if it does match up. And I guarantee you, again, it should match up. So let's do it really quickly here. So -1 over 5 is my a value. And then I had x plus 4 squared and x minus 2 cubed, and let's hit graph. And so I don't see the top there. My top end should be somewhere in the 60, higher than 60 there. So I'm going to change my y value to, let's say, 60. I don't want to go up by 1s by any means. Let's go up by something like 5s. And there we go. We have the exact same shape. You don't necessarily need that second line there, but we have the exact same shape. We're hitting the exact same y or x-intercepts and the same y coordinates. So if you hit trace, 25.6 should be your y-intercept. On the next example here, this is a bit of a word problem, so hear me out on this one. So we got the width of a box is 15 centimeters greater than the height. The length of the box is 20 centimeters greater than the height as well. The volume of the box is 2,500 centimeters cubed. Okay, so write down the polynomial function that represents the volume of the box. Well, let's figure out what our height, width, length, and height is. So I'm going to start off by saying height. I'm going to call it x, just because everything is compared to height. So we got the width of the box is 15 greater than height, and the length of the box is 20 greater than height. So height, let's just call it x. So then the next one here I have is width. And let's work on width. Width is 15 centimeters greater than the height, so I'm going to go height plus 15. The length, th there, equals the length was 20 greater than the height, so length is x plus 20. And I know that my volume of the box is all three of these multiplied together equals 2500, so let's set that up. So I got volume equals length with height. I know my volume, of course, is 2500 is equal to x times x plus 15 multiplied by x plus 20. So there we go. We wrote a polynomial function that represents this box. Done. Up next, find the actual dimensions of this box. So let's go to our graphing calculator to do this. So on my graphing calculator, I'm going to type in my equation. So again, I had x, x plus 15, and x plus 20. That is going to be my y1. My y2, 2500. Double check your window setting on this one. Double check your window setting. So my window setting, I'm going to change just to make sure that I can see everything. Right now, let's go zoom 6, so normal window setting. See one line going up, probably not good enough. I'm going to look for more x's or more y's. So I'm going to just add a 0 everywhere just to play around with my window setting, just so that we can try to find what our graph looks like. And once we do find it, we'll refine or we'll cut down on this just to make it look a bit nicer. So there we go. We have a squiggle right there. So we probably don't need it as much as I have set up. So this is now 5, 10, probably 15, 20. So in my window setting, instead of -100, I probably cut it down to -50 there. To +100, I don't have any blue lines on that side, so I'm going to go +50. -100 was too much of an overkill there, so I'm going to drop that down to just -50. And 100, we didn't quite see the top, so let's bump that up. Let's go to something like a 250 marker. And there we go, we do see the top. Oh, I do want to see the bottom there because I think I dipped it down a bit, so let's change that back to, let's say, something like a 150, and here -150 if you want to try to see your full graph. And there we go. And again, we still don't have quite the bottom there, but this is kind of good enough. Right now, what I want to find is all my x values, because we're looking for x. And I want to find y equals 2500, by the way. So I really should play around with my window setting a bit more. I'm going to go straight up to 2500. I'm just going to go a bit past it, 2600 there. Let's go up by 100 here. Hit graph. That intersection is what I want to look for. Second trace, option 5. I'm going to move my cursor as close as I can there. Enter, enter, enter. At 5 for x, we have a y-intercept of 2500. So find the dimensions. So if I know what x is, if I know x was 5, so therefore we have x equals 5, so then that's my height now. My length and width, so my width and my length, my width was x plus 15, so now this is going to be 5 plus 15, just now width of 20, and my length was 5 plus 20, which is now 25. So let's double check our volume real quick. So our volume is all three multiplied together, so we got 5 times 20 times 25, and I'm hoping this matches up to 2500, and it really does. So there we go, we are good. So my length with height was 5, width is 20, length was 25. Of course, units on all of them should carry the units of centimeters. So height was 5 centimeters, width was 20 centimeters, and length was 25 centimeters. There we go. On this next one here, this is straight from good old 10C mathematics. This one says you have a box with a lid with no a box with no lid right there. Is made from cutting 4 squares out from each side. You have dimensions of 10 by 20, so what is the volume? Find an expression that represents this volume, and this was from 10C, if you can you imagine. So our volume is going to be length times width times height. So volume is going to be 20 minus 2 x's that you cut off there, so 20, and this would be x here and x here that you just cut off. So that's my length. My width would be 10 minus 2x, because again, here's an x and there's an x right above that you would have also cut off from 10. So that's length, that's width, and my height, just x. Here it says sketch a graph of your function and state the restriction. So notice that my graph here is between negative 200 and 200 for y's, probably negative, looks like negative 2 to 10 for x's. So let's set up something similar. So first off, type in your equation. So we got 20 minus 2x times 10 minus 2x times x. And I use brackets for all my multiplication, of course. My window setting, again, was from negative 2, it looks like, all the way up to 10 or 11 there. So let's go to 11 just a bit further. X scale was going up by ones. My Y scales is from about negative 250 there, it looks like, all the way up to positive 250. And the scale here looks to be going up by 50. Hit graph, and that's our curve there, done. And you're just going to go second graph and pull off as many of these values as possible to sketch this graph as best as possible. And that's my graph. Oops, I have an extra little piece. So that's my graph, more or less done. Here it says to sketch the graph, which we have. State restrictions. State restrictions on this. What's our restrictions? So let's talk about our domain. What can our domain be? Our domain can only be between here and here. It can only be positive values. You don't want a negative domain because that won't, you can't have a negative volume overall. Okay, so domain, you want a positive because you want to stick to this x value or a y value here, which is a volume that's positive, so you want a positive domain. So our domain looks to be between 0 and 5, positive 5. What's our range? And again, you want a positive value because our range is associated with our volume. You can't have negative volume down here or here, so that doesn't make sense. So our range, you want it to be between greater than 0 but less than whatever that top end is, and I believe we went up by 5, or we went up by 50, so 50, 150, probably less than 200 there. on this first section. And again, 200 is pretty generous, including 200 there. And again, I'd be guessing I want to find that max value there. But notice that we also have a bit further off to the right here, our graph continues on. So we can play around with that there. But between 0 and 200 it looks about right. Find the x value to the nearest hundredth that will maximize the volume of the box. So basically this is asking you find your maximum here. And if you can't remember how to do this, as a second trace, you have a maximum, option 4. I'm going to bring my cursor to the left of where I think the max is, hit enter, bring it to the right of where I think the max is, hit enter, and let's find where our absolute max is, and it's around there. I'm going to hit enter as my guess. There's my maximum, and this here is part C. This here is going to help us for part C. So let me just shrink down my graph just a bit to fit it in. So for part C, it says the value of x to the nearest hundredth, so that means 2 decimals. What's x equal to? So we have x equal to 2.11. That will maximize the volume here, so our max volume is looking at 192 there for our volume. And last but not least, it says what's the max volume of the box, and I literally just found that off of my graphing calculator. So we have a y value equals 192, and again let's go to hundredths, 0.45. So that's going to be my max volume. So I could say something like max volume max volume is equal to 192.45, and the units on this should have been centimeters cubed, because all the units in this question were in centimeters. Volume, of course, something centimeters cubed. And that's the last one there. If you have any questions about today's lesson, please feel free to ask.